Alright, so just as a reminder of where we were solving this differential equation, this differential equation by complexification, meaning you embed this problem into a larger problem, right, with making it complex on the right hand side. And so by making this the complex exponent, we can guess then that our particular solution is also of that form. And I just was pausing here for a note that the homogeneous part of the solution would not match, right, the complex conjugate or the complex right hand side. Good. So therefore, let's see, y sub p prime is 3i. Just go ahead and differentiate as if it were a constant, and then we differentiate twice. Plug those into our differential equation. Solve for the constant a. Okay, and then we found that because the original function, the original right-hand side, was the cosine of 3t, what we want, which is the real part of e to the 3it, then at the end you want to take the real part of ae to the 3it. Okay, and so how do we compute that? That's where we're at now. And so we just have some arithmetic to do here. It's not too bad. Okay, so I just took a moment here to write out what my computation is, right? I got 1 over minus 8 plus 6i, and then I multiply that by the conjugate to get the real part, or to get a real number in the denominator. And then I multiply this all out times cosine of 3t plus I sine 3t. Just as a quick computational note here, this front constant becomes minus 8 minus 6i divided by 100 times cosine of 3t plus I sine 3t. And I can simplify that before I get started. Let's go ahead and cancel out the 2's, right? So that would be minus 4 over 50 minus 3 over 50i, right, times our cosine of 3t plus I sine 3t. Okay, and so now if I multiply that out, actually I don't need to multiply the whole thing out. Oh, let's go ahead and multiply the whole thing out. What the heck? I'm going to pause this and write out what the whole thing looks like. Good. Okay, so if I FOIL this all out, this is my real part, and this is my imaginary part. And so now we have our full y sub p, and our y sub p ends up being minus 4 over 50 times cosine of 3t plus 3 over 50 times the sine of 3t. Good, and we're done. That was fast, wasn't it? Hey, before we finish this, remember that we can write this as r cosine of omega t minus delta, right? So can we go ahead and rewrite that? Do you remember what the r and the delta was? R is the square root of minus 4 over 50 squared plus 3 over 50 squared, right? And then the delta is the argument of minus 4 over 50 plus 3 over 50i, if you want to think about it that way. Okay, and so what do we get if we simplify that? Let's see, that's 64. Oh, 16. 16 and 9 is 25 on the top, right? 50 squared on the bottom. So we get 1/10. All right. And then, this is going to be, delta is the inverse tangent of, well, you could write it as 3 over negative 4 because the 50s will cancel, right? But I wanted to emphasize one thing, and that is that this r is also equal to 1 divided by the the magnitude of minus 8 plus 6i. And then the delta is also in the argument of minus 8 plus 6i. And so if you recognize this, where did the minus 8 plus 6i come from? That was here, right? So what we're saying here is that there's a nice shortcut here for computing the solution to this. What we're saying here is that given, let me switch over. So given that your constant A is equal to 1 over alpha plus beta I, then to write y sub p as r cosine of omega t minus delta, we just take r to be 1 over the magnitude of alpha plus beta I, and delta is the argument of alpha plus beta I. Good. And so this is a real shortcut here, because now we don't have to do all of this stuff that we did up here. Okay, and so that's a big time saver. And in fact, let's go ahead and solve a differential equation using this little time saver. All right, so here's the differential equation that I want to solve. It looks a lot like the other one, but it is different. Y double prime plus y prime minus 2y equals cosine of 2t. And then I'm going to write the result as r cosine omega t minus delta. Okay, so we already see, right, that the omega is equal to 2. And so I'm going to go ahead and write my ansatz as ae to the 2it, right? And so the right-hand side here I'm thinking is going to be e to the 2it. Okay, so then the derivative, let me write yp equals, so that yp prime is going to be 2I times ae to the 2it, then yp double prime will be minus 4 ae to the 2it. Good, so plugging those into the differential equation and factoring out that ae to the 2it. So for the second derivative, I'm going to have a minus 4 plus, this is just a 1 here, so that's going to be 2i minus 2. That's equal to e to the 2it. Good, which is what we transform the right-hand side into. Therefore, a is equal to 1 over minus 6 plus 2i. And that pretty much finishes this off, right? Because now we can say that r is equal to 1 over the square root of 36 plus 4, 1 over the square root of 40. Should we simplify that? 4 times 10, right? 1 over 2 square roots of 10. Okay, and then the delta is the argument of minus 6 plus 2i. And notice, by the way, that minus 6 plus 2i is in this quadrant here, right? Quadrant 2. And so therefore, we're going to have the inverse tangent of 1/3, or minus 1/3, plus pi. Okay, so that's what our delta is. Now we have our r, and we have our delta, and so therefore the particular part of the solution can be written as 1 over the square root of 40. Well, I simplified that. 1 over the 2 square roots of 10 times cosine, that's what we were doing. I had to think about that for a second. Minus the delta. Okay, good. All right. So I think in the next video what we're going to focus on is we'll just focus on examples, and we'll do several examples in the next video, just in case that anything looked a little funky. Okay, see you then.